What you got there, Mr. Bergman?
Oh, I've got a flask that's completely full.
Yeah.
Yeah, and you see it's full?
I'm pretty sure it's full, yeah.
Yeah. What's it full of, Mr. Sams? A lot of students think this is an empty flask.
No, we don't have a whole lot of empty things around here. It's full of gas,
Yes,
full of air.
you see, guys, if you look really close in here, you'll see gases. Actually, you don't see the gases, but they're there. And these gases are ideal, okay? We're going to learn today about what an ideal gas is, but primarily what's in here is oxygen and nitrogen gas. And here in Woodland Park and really anywhere on the earth, the main gases, they act as an ideal gas. And we're going to learn about what ideal gases are today.
We're talking about the ideal gas law today, Mr. Sams.
Yeah, I'm ideal.
You're ideal.
I am.
You're ideal?
Yes, I'm the ideal specimen of mankind right here.
Look at that face, boys and girls. You think he's the ideal
yes.
specimen?
Exactly.
What do you think of, like, Brooke Shields or whatever? I mean,
What decade were you born in?
Oh, a long time ago.
Yeah,
Brooke
these
Shields.
kids don't even know who that is, probably.
Probably not. Okay, not Brooke Shields was the girl. So I'm trying to think of who was the guy back then. See, I had this crush on Brooke Shields when I was a boy.
I can see that.
Yeah. But anyway, she was the ideal specimen of female.
They
kind
all pale in
those days.
comparison to me.
Oh my, Mr. Sams, I think we need to knock you down a little level. All right, let's talk about this thing called the ideal gas law. It's actually derived from the combined gas law. And so the combined gas law, as you recall from the last podcast, was this: P1 V1 over N1 T1 equals the same thing with the twos.
The twos, yep.
So what we do is we just rearrange it.
Right. Now, all the previous gas laws, we've been talking about a change in conditions. You have an initial something and then a final something. Yes. So let's assume we have a gas that's at STP.
Okay.
And so
STP, what's that mean?
Standard temperature and pressure.
Okay.
And we have 1 mole of that gas. So we'll plug that data into our ideal gas law.
Okay, so copy this down, guys. Basically what I did is I plugged in for the pressure 1 atmosphere.
Because that's standard pressure.
Okay, and then kind of tricky here. There's 22.4 liters in a mole.
Right, and we've learned that. We've done lots of stoichiometry with that. That's how many liters per mole of a gas at STP. So we're just going to plug STP conditions as well as the number of moles and number of liters into into the combined gas law.
And if you take this number right here, 1 divided by times 22.4 divided by 273 divided by 1, you get a kind of a famous number we're going to say here. So what you get here is you get 0.0821.
Now that's some funky units it's got there.
Well, I know it's kind of weird. It's liter because of the volume.
Okay.
And then atmosphere because we used atmospheres over here.
Yeah.
And then we had moles, of course, and then we have Kelvin.
So liter atmospheres over mole Kelvin. That's the units for it.
Yeah.
Okay.
So that's what that is. So I rearrange this equation. I can then say PV equals nRT.
Where do you get R?
Well, R is actually this number right here. This is a famous number. Sometimes scientists give numbers letters, and they're famous numbers.
Okay, so whenever we see R, we're going to put 0.0821 if our pressure is in atmospheres.
Right. And so what you really need to do when you do problems of this variety is convert your pressure into atmospheres and your volume into liters, and your temperature into
Kelvin.
Kelvin. Always think Kelvin. Kelvin.
Always.
Always.
Kelvin.
Always Kelvin. All right. So, hey, let's do an example.
All right, let's do it.
So we've got our scuba diver here. In fact, I picked the scuba diver as the background because that's pretty cool. But let's say that scuba diver, here's the story here. It's containers filled with 0.25 moles of oxygen gas. We have 0.25 moles of oxygen gas. With a volume of this many liters, we want to figure out what is the pressure of the gas in his scuba tank. So let's do that, okay? Well, I've kind of cleaned the screen a little bit here just so we can kind of figure this out a little easier.
Our calculator has feet again.
Yeah, our calculator has feet because guess there, what do you have there? You have Mr. Moleman. Okay. All right, so we have container filled with 0.2. Actually, here's our oxygen gas. So let's kind of put our conditions here. And so we have 0.25 moles. So I'm going to say N is 0.25. What else do we see there, Mr. Sams?
We got a volume.
V. Okay, what's that?
2.35 liters.
We're just getting that, guys, from the text up here.
And temperature is 45 degrees Celsius.
Now, Celsius doesn't work very good.
No.
That's all right. And then P equals...
Question mark.
See, we're trying to find that. So we'll put
and
a question mark.
R.
R. Well, let's go ahead and write that. That's 0.0821 liter atmosphere over mole Kelvin. Now, we're just going to use the ideal gas law.
Plug and chug.
Which is PV equals nRT. Now, we're solving for P. Now, you can kind of rearrange it if you'd like at first, but I think it's just easier just to plug it straight in. So I want to say P, because that's what I don't know P, times V. What's V?
2.35 liters.
2.35 liters is equal to N. There's my N. 0.25 moles. I'm going to run out of space, aren't I? Times R.
You can always move the calculator.
Yeah, actually, I think I will. I'll move the calculator down here for a moment. Times 0.0821 liter atmospheres per mole Kelvin times my temperature. Now, a little tricky thing on the temperature. The temperature needs to be added 273 because you must always put it in Kelvin. Kelvin, man. All right, let's put the calculator over here. Oh, that was kind of weird.
318.
So when you add those up, you get 318. So we'll say 318. Now, when you divide both sides to get P, right? Now, you guys, you algebra people, what do? You divide both sides by
2.35.
2.35. So if I divide by 2.35, the 2.35 cancels here. So now on my calculator, I have 0.25 times 0.0821 times 318. I forgot my units. Mr. Bergmann, you're naked. Okay, and this would be in liters. Divided by 2, backspace. How do I backspace? 2.35. Bingo. I get the answer. So the pressure is 2.78. So what would the units on that be, Mr. Sims?
Well, let's cancel them out up in the top and
All right,
figure
so
it out.
the liters cancel here and here. We've got moles here and here. That cancels. And my Kelvin is here, and that cancels.
That
and that
leaves
leaves
us
you
with atmospheres.
atmospheres, yeah.
There it is.
And that's because if you're using this equation, typically pressure will be in atmospheres. I think we should do another example, Mr.
Let's do
Sims.
it.
All right. Let's take a look at our next example. Okay, example number 2. Okay, we've got this in the way. All right, 15.3 grams of ammonia is placed in an empty 2-liter container. The pressure is measured at 925 millimeters of mercury. What will the temperature be?
Okay. So same thing. Now, you'll notice when we're dealing with the ideal gas law, our conditions are not changing. We have one set of conditions, and we want to know one of the variables at those conditions. If conditions are changing, you're going to use Boyle's law, Charles' law, Gay-Lussac's law, combined gas law. But if you just have one set of conditions and they don't change, ideal gas law.
Ideal. Okay, so what do we know here? We've got 15.3 grams. Wait a second.
Yeah.
Well, let's do the P and stuff. P, PV and RT. What's P?
925 millimeters of mercury.
925 millimeters of mercury. And actually, let's just talk about this. That's not the right unit, Mr. Sands.
Nope.
We've got to convert that to
Yep.
atmosphere. So remember, we can just say there's 760 millimeters of mercury in 1 atmosphere. Okay, so let's get our calculator out. Let's just do it right here.
Okay.
So 925 divided by 760 gives me 1.22. So we've got 1.22 atmospheres. All
Okay.
right, V equals, all right.
2 liters, 2.0
All right, there it is right there, 2 liters. And we like that. That's the unit we're happy
Yep.
with. PV equals N. Okay, so N's the next.
Yeah, we don't have N, but we have grams.
But we do have
and we
15
can turn grams into
yeah.
moles quite easily.
So actually, we're going to write 15.3 grams over 1, and we're going to use the fact that ammonia is NH3, and then we're going to say grams in 1 mole. And I'm going to look in the periodic table, find the molar mass of N, or atomic mass of N, and the atomic mass of hydrogen, add them up, and I get 17, and I can just do that right on my calculator over here. So I'll just take 15, I need more space, don't I? So 15.3, a little bit less than 1, won't it?
Yep.
Divided by 17 is going to give me 0.9, 0.9, actually 0.900 moles, because this is actually 17.0 and we have 15.3. Okay, R, we know R, 0.0821 liter atmospheres per mole Kelvin. And T, I believe, must be what they're asking for us.
That's your unknown. Yep.
What
is
will
the temperature?
be the temperature? And so that's what we're trying to find.
Okay.
So I'm going to move this over here. I think it'll make it easier. So I'm going to say my P is 1.22. So 1.22, that's P. I take the numbers out so it's easier to, we're just going to look at numbers. V is 0.900.
Nope.
Oh, that's R, or N. PV. V is 2.0 liters equals R in 0.900 times R times T. And we know R is 0.0821. So divide both sides by what, Mr. Sams?
0.900 and R.
So 0.900 R. Now, let me show you something on your calculator, guys. I'm going to do something pretty cool right here. I'm going to take 0.0821. I'm going to push this stow button down here. I'm going to stow it. I'm going to push the alpha button here. and I'm going to find the R button, which is right here, the times button. Okay, and what I've just done is I've stored into the R button the number 0.0821. So every time I put in R, I can it saves that number. I don't have to remember it all the time.
Yeah.
Sometimes it gets erased and you have to redo it. So now what I'm going to do is take 1.22 times 2 divided by 0.9. Now those are both on the bottom, so don't forget you're going to say divided by.
Don't hit times there.
If you hit times, you'll be all screwed up. Divided by alpha R. And I get this number. Wow, that's pretty cool.
Yeah, it is.
T equals 33, and that's going to be in what units?
Kelvin.
Kelvin. That's very cold, Mr. Sims. 33 Kelvin is a very, very, very cold temperature.
Yeah, that'd be. I would actually be surprised if ammonia is still a gas at 33 Kelvin.
My guess is it's probably a liquid. But that's how you solve that problem. Okay. All right, let's look at the next example. Oh, no, we're done with it. Okay, we can take away the calculator because that's it. All right. Now, deviations from ideal. You know, Mr. Sims, I have an ideal family. I think I can say that.
What?
Look
how little they are. They're so tiny.
Yeah, actually, this picture's like way too old
No
because, you
kidding.
know, this is Caleb, and you know where Caleb stands? He's about this tall right now. So Caleb is like huge. My oldest son, who's now a
He's
junior
almost
here.
my height now.
He's 6 feet tall. So this would be Caleb today. Emily is at my height, and Katie's still kind of short. She's right here. So, but she's getting taller. So these, oops, that's a Katie. This is Emily.
I was going to say, wait a
I
second.
got them
thought-
mixed up, but she's actually, it's more like this. She's going to be my basketball player. Okay. Anyways, but they're ideal, but are they perfect?
No.
No. I will confess that my family is not perfect, but they're kind of ideal because ideal means it's close enough to perfect.
All right.
Yeah. All right. So what is an ideal gas? One that's
Close
enough to perfect.
Right.
Okay. So ideal is, well, like I said, ideal is close enough to perfect. Okay. Now let's talk about it really. What does it mean when I say, what does an ideal gas have, or it has? It has two things, two very important things. Number one, it's not attracted to itself.
Okay, we talked a little bit about that in a previous lesson. I think that was 7.1, where the molecules do not attract nor do they repel each other.
So I
they
have
basically
two
just don't interact.
Molecules, there's no attractive force between them. They don't
Right.
like each other, and they also don't push away each other.
Right. Now, in reality, they do, but it's such an insignificant amount at the conditions that we measure gases in that we just ignore it.
Right. And secondly, they take up no space.
Right,
Now, this
so-
is a weird one to get your mind around.
Yeah, we're assuming that the gas particles are so tiny that the space that they occupy is insignificant compared to the space in between all of the molecules.
So in this box that I've just drawn, I have gases. Now, they take up the space of this box, but the actual volume of the sphere of the gas is insignificant, or we consider it to be zero if it's an ideal gas. And that exactly is not zero. But think of it this way. Let's say if I have in this room, I'm standing in a large classroom, and I found 2 marbles in this room, which is actually probably even too big. But let's just say for the sake of it, 2 marbles. Do they take up any space in this room?
They do, but it's so insignificant compared to the size of the room that we really don't care.
So that's what we're kind of getting at.
Yeah.
Okay. All right. So there is actually another thing is ideal gases don't really exist.
Right.
But they're close enough.
Right. You know, there's one other factor that's not listed here, and that's when the gas molecules bump into themselves
Yes.
or to the sides of the containers, we assume that there's really no energy transfer, that it's
Yeah.
a completely elastic collision,
Yeah.
is what we say.
Scientists call it elastic collision.
Right.
And this is actually how we can look at an ideal gas graphically.
Yep.
When we look, oops, I wanted to stay there. I thought I had a thing there. So if we look at it graphically, what we've got here is that depends on a couple of things. The, you know, this is important. I don't think for these
Nah.
guys. I think
Just at the conditions we measure gases in, they're going to be close enough to ideal.
Okay. But here, if I want to make a gas ideal, now we talk about gases in this room, like at the beginning of the podcast, oxygen and nitrogen, but there are gases in this room that are not ideal
Right.
because
They're highly compressed.
they're highly compressed or they're
Right.
actually got very attractive forces. Like
Right.
water vapor is not ideal in this
Right.
room. But how could I can make any gas ideal though.
Yeah,
Any
if you get
gas.
the pressure low enough,
Yeah.
and
So I can
the
take
temperature.
I can take this pair of scissors right here, and I can take this pair of scissors and I could melt the scissors. They're made of iron, and then I could heat them up, and I could turn them into a gas.
You could.
And then I could make them ideal.
Okay.
But I would have to make them ideal. I would need one of two conditions: a very high temperature. So I can make anything ideal if the temperature is high. Now, when I say high, I mean high in comparison to the boiling point of that chemical.
Right.
So in this room, oxygen is ideal.
It's a lot higher than its boiling point.
Its boiling point is minus 200 and something degrees Celsius. We are 200 and something. We're like almost 300 degrees above that in this room. Now, if I wanted to take the scissors, if I could get it 300 degrees above its boiling point, which I don't know what it is, I could make it ideal. Right. Second thing that would help it is if I could have a low pressure, so they're more spread apart.
Yep.
So if the gas particles are further spread apart, look at the picture over here. If these gas particles are a long ways away, then they will behave in a more ideal fashion. So, guys, the moral of this point of the story is that ideal gases can be, anything can be an ideal gas if you have a high enough temperature and or a low enough pressure. Key thing really is the temperature. Give it above its, so it's way above its boiling point. Okay?
Okay.
I think that sums up ideal gas laws. You'll do some problems. Very easy worksheet in this unit. So, okay, so we'll see you in class.
Bye.
See ya!